Okay, here's the overview. We'll first talk a little bit about model learning and the difficulties of model learning that can also arise. Then I'll introduce an approach from the 90s, back in the 90s, that was introduced by Rich Sutton, which is called DINA. It's exactly this combination that I was talking about, learning a model, dynamics model, and then using it to generate artificial data to train a Q function, for instance, in addition to the real data that we use for the Q function. And then we'll look at simulation-based search, and in particular Monte Carlo tree search a little bit. That is, one of the key ingredients, key components also of this AlphaGo system that we saw in the very beginning, that had this great success in computer Go. Okay, right. Again, slide contents are heavily based on the Sutton and Bartow book, and also some figures from David Silver. All right, let's remember real quick the components of an RL system. By now you're quite familiar with it, of course. We have the policy that can be stochastic or deterministic, maps from states to actions or action distribution. We have the value function that defines the expected value of being in a state and also taking an action, particular action in the case of a Q function. And now finally we'll address also models that we want to learn from data. So we don't assume, like in dynamic programming or in the MPC lectures that we've seen, that we have already an identified model, but we basically want to identify one, so from the data. And that will give us then this transition model, probability distribution over potential next states and next rewards that we might get, given that we are in a state S and we execute an action A. Yeah, so it's really just, you can't see the cursor? You can now, good. It's this probability of this S prime and R, given that we were in state S and executed action A. All right, now it's actually the case that, for some tasks, learning models is very easy, and for some tasks, it's really not. It can be very difficult. And you, of course, need to make abstractions. A model is always an abstraction, but hopefully a useful one, of course. And it depends on the problem, whether it's easier or harder to learn a value function or a policy, or generate a model and then use that to optimize your policy. The nice thing, if we think about this problem, if we see this as a prediction problem and a learning problem, then this is a one-step prediction, right? We have state S, we execute an action, that's our inputs, and we want to know what's the most likely next state, for instance, if we're just optimizing for the maximum likelihood solution, or basically do a deterministic, pretend we have a deterministic model and we don't care about a whole distribution of possible next states. And this can be done with supervised learning, right? So we have this information. It's basically a self-supervised learning problem. So we are in a state S, we execute an action A, and at the next time step, we will know what is ST plus 1, right? That's the next measurement that we get if we assume that we can really observe the states. And then we can use that for training. We make a prediction for ST plus 1, so ST plus 1 hat, and then we can define an error to the real ST plus 1 that we observed, right? And we can use that in order to train a prediction model. So that's nice, because it's, in general, often a much easier learning problem. If we're just doing this one-step prediction ahead, it's a much easier problem than predicting the value at the end of a very long or potentially infinite horizon, right? So in that sense, it's usually an easier learning problem. But for some problems, the models or the physical system that we're dealing with is, of course, also quite complex, right? And it can be more complex than, for instance, a policy or a value function. Right, so here, this is a little comment that it can be easier to concentrate on state changes, so to predict changes rather than the absolute states, tends to generalize better if you want to train a model. But in general, what we can say is that these model-based algorithms, yeah, where we learn this model explicitly, they tend to be more data efficient. So they require less samples, less interactions with the environment in order to already produce good solution, intermediate solutions. Yeah, and that has to do with exactly that we can use rather simple, for instance, neural networks, let's say, or some simple function approximator to solve or train a good model for this one step ahead prediction. We don't need to have huge models usually, and that also means they should learn better. Yeah, they should learn faster, and make more progress on this easier task of one step prediction. But how on the other hand, they're of course then also a little bit limited, or they can be limited. Because of this simple structure that we might use for these models. And we have to do additional work to extract an optimal policy from them. Moritz told you all about how to use models in order to extract good policies, yeah. But it's of course, you need to do a lot of optimization for that, right? Whereas if you train a value function, then you usually require much more data. It's much less data efficient. And it's much, you need to train for a very long time in many cases, but then once you have trained everything, then you basically just have to run a forward pass through a neural network from state input to an action, and then you're done. You have your action. Okay, and well, learning a policy tends to be also data inefficient. Yeah, so these policy gradient approaches tend to require much more data also than these value function-based approaches or these model-based approaches. You can, of course, combine them in various ways, right? You can actually have learn a model and use that also to optimize policies. So there's also things that you can do there, and then things get more data efficient. Yeah. Okay, and just as for an example, maybe consider these two things down here, this little maze on the left side, which is rather complicated if you look at it. So I think you enter somewhere here, and you exit somewhere here, and then you need to find your path in between, right? So this looks like a very convoluted and very long path that you might have to go through with your agent. And here, learning a value function for that requires many steps that you need to get right here and that you need to explore. So this is a rather long horizon over many steps. So this tends to be a rather hard problem then to learn a value function. Whereas if you would learn a one-step prediction model here, the environment itself is very simple, right? So you have these simple rules where you can only execute these 4 actions maybe, and in some states maybe you bump into a wall and then you don't change your state, and so the interaction dynamics are relatively simple compared to some real system, of course, right? And if you consider the example on the right side where you maybe want to grab a coffee cup that already has some liquid in it, if you were really to model the mechanics of the hand exactly with all all the fingers, the friction, and also maybe consider the liquid and how it changes when you grab it and you take it up, and all, I mean, you could go into very much detail and build a very sophisticated and elaborate model to really capture the physics of what's going on. But if you think about the policy, getting close to the cup is easy, relatively easy with your arm. And then, once you're close to the handle, all you need to do is basically close your fist, if you like. That's a reasonably good policy. And it's simple, if you think about it, compared to modeling all these physics of what might be going on there. So for different problems, different things make sense, right? Learning different things. Okay, so if we have a state and an action, then our model would generate the next state and also the corresponding reward. And you can do that either predicting all possible next states in a distribution, probability distribution over next states, or just the most likely one, would be called a sample model. Maybe just a quick question, which one did we use in dynamic programming? I mean, I think we used both. I mean, you concentrated on deterministic models, right? But I mean, here, maybe I'm answering this myself. So I mean, what I was getting at here is that in general, in these dynamic programming equations, these update equations, we have these expectations, right? So there we actually need to know a whole probability distribution in order to calculate the expectation. Yeah. Okay, but there are different ways you can approximate these models. And then if you want to extract a policy from a given model, from a model that we've learned, we would usually call that planning. And the sort of workflow would be that you have a model, yeah, maybe very bad in the beginning, just randomly initialized, maybe with its parameters. You generate some simulated experience. You generate backups for the values of a value function, and from that value function, then you extract your policy. Yeah, that's one potential way you can use a model. It's not the only way, as we know. You can directly use a model to extract a policy, but this is one particular way, and it's a way that has been very influential in the reinforcement learning community, especially with this DINA approach that I'm going to present, but also in other contexts. Okay, so with planning, we refer to using the simulated experience that we generated with the model, and learning usually refers to using real experience from the environment, but we can, of course, also apply learning. We want to learn a model from the real experience, right? Okay, and that's one way to do that. A simple way that we could do is this so-called random sample one-step tabular cube planning, where we just loop in an infinite loop. We select the state S and an action at random. Then we would send S and A to some sample model that would predict the most likely next state, and also sample reward. Yeah, so S prime and R prime come from this model that we're learning. And then the model that we have, actually we don't improve the model in this case, we just rely on a model. And then we apply one-step tabular Q learning to this tuple of S, A, R, and S prime. Yeah, so this then just is the Q update here as we had it in Q learning, okay? So that works, and it will converge to an optimal policy in the end, optimal Q values, and then you can extract the optimal policy from that. But it will converge to the optimal model for the optimal policy for this model, right? And if the model is wrong, then of course it will converge to a solution that's not optimal for the actual real process that we want to interact with. Okay, DINA, on the other hand, improves the model over time. And it will use the model to basically bootstrap the Q function with imagined or simulated experience. Yeah, so you use the real experience to optimize your value function just as before, or the policy if you're directly training also a policy, and then you can either optimize the value function directly. That would be model-free RL, yeah, that's what we saw before, or indirectly using the model to generate artificial data. Yeah, and as I said, these indirect methods, they tend to be more data efficient. You need to have less real interaction with the real model because you can, in between, once your model is trained to a reasonable degree, then you can generate data that is useful already to train the value function and produce reasonable estimates. But of course, these models are initially very wrong. Yeah, you just initialize them randomly, and they therefore also introduce another source of bias into the whole learning process. Okay, but DINA tries to combine these ideas, and this is what it looks like. You have real experience, yeah. So you start with the data that you gather with the real system, and you use it both to update your policy or your value function, okay? But at the same time, you also train a model, yeah? So you do the self-supervised learning to, for a given state and a given action, learn to predict the most likely next state. And then you can use that model to do search, right? You generate simulated experience. So you roll out some policy with the model, and you observe what states and what rewards you would get, if your model would be correct. Or basically, you just ask your model, so what do you say? Like, here's what I would execute, what states and rewards would I see? And then you just pretend that's real data, and you use that as well to train your value function, and in the end also your policy. So that's the idea. And the way that it's implemented is, again, rather simple for the tabular case. This DynaQ algorithm, what it does is it has a Q function, and it has this model. And again, that can be some kind of function approximator, some kind of statistical model, like a Gaussian process or something like that. And you just get the current state, and you derive an action epsilon greedily from this state S and the Q function. And then you would take this action A in the actual environment, in reality, and you observe what kind of reward and next state you will get. You use that to train your Q function, just as we had it in Q learning. But now, of course, you also want to improve your model. So you use that real data that you've just gathered in order to improve your model. So here's just a sample model. We assume a deterministic environment, and then for this one real step that we take, we can take n simulated steps. Basically, we would trigger our simulator n times, using the learned model. So we get some random previously observed state. So we look through our experience that we've gathered, and we randomly choose an action S, state S, in order to just make sure that we have some experience in that region, and our model generalizes somewhat in the region. And then also we would take a random action that we've seen previously in S, and then we would just roll out this S and action A in model S, and observe what kind of reward and what kind of next state we would get. And as our model changes, of course, then it will do different predictions over time, right? And we generate hopefully more and more accurate data for the model. And that artificially generated data, that artificial R and S prime, is then again used to train the Q function. So that's what I meant before with bootstrapping the Q function with this artificial data. Okay. And again, think about it. So since we said that models are in many cases much faster to train, because they address a simpler learning problem, we can really make very quick progress on learning a reasonably good model, and that can help us, for instance, really in the initial stages of learning the Q function. Well, when we don't have so much data yet, so much real data that we can use, then we can make much faster progress using these artificial data as well. And actually, so it's an interesting question to ask, if this is true, this assumption that I just mentioned, that learning a model is usually easier than learning a Q function, and it's good to rely on a model in the initial phases of learning, and then maybe switching over to model-free learning after you have enough data. One question that is interesting to ask is, when is the right time to switch, or to rely more on the model-free side and less on the model-based side, for instance? And that's actually something that we addressed in our research also. And maybe if I have time at the end, I can come back and show you what we did in that respect. But for now, just I want to illustrate how Dyna actually performs in a simple environment here. So here we have this little grid world that you see here. Some start state, some goal state, and in between some obstacles. And the agent needs to get to the goal as quickly as possible. And then you see the number of steps per episode. So, in the beginning, the agent takes very long to actually get to the goal. And you see in the blue curve, this is 0 planning steps, 0 simulation steps in between with the model. So it's just model-free RL, as we had discussed before. So this is then just Q learning, basically. And with 5 planning steps, you get to the screen curve down here. And if you interleave 50 planning steps, 50 updates with your model, you get much faster to a good solution in this simple example. So this can make quite a big difference of using this model. Okay, let me stop here for a second and see if there are questions. Yeah? Can we stop the recording right now? All right. Yeah, so the model might be wrong, of course, can be incorrect because you usually don't get perfect models. We only have limited number of samples. Your environment may even change and your model may not have captured it. And also, I mean, for the more complicated tasks, we use function approximation. And yeah, we do things like stochastic optimization, and there's inherently noise and imperfections in the model. Also, yeah, especially, of course, we can't expect that in areas of the state and action space that we haven't explored at all, we can't expect the model to generalize well, right? Even if we have a smooth function approximator, yeah, where we don't have any data, then we can't really hope that the model can generalize well. Right, and that's also why we have a distribution mismatch. If there's, for instance, regions of the state and action space that are quite different in the dynamics from each other. Yeah, so think about a task where a robot has to learn, a robot arm, for instance, has to learn to, first get to a puck or something, or some object, a cylinder or something, and then it needs to shift it to some goal region. Yeah. So there's in the Mujoko and the OpenAI gym, for instance, there's a little benchmark task that's called the pusher. That's exactly that. So you have an arm and it needs to learn to basically push a little puck into a goal region. And so what the robot first will learn is to get close to the cylinder, yeah, to the puck. And then all of a sudden it has contact, right? It has contact with the puck. And then the dynamics are quite different from when it just goes to open space and tries to reach that object, right? And you can really see that when you try to learn a model for that. In the beginning, you make a lot of progress just trying to get close to the object. But then once you start interacting with it, there's a jump all of a sudden. The performance gets much worse again. And then only over time, as it interacts more with the object, the performance gets better again. Yeah. So when the agent enters new areas of the state action space that has quite a different dynamics, for instance, there will definitely be a distribution mismatch. And of course, yeah, if you have a wrong model and you use it to generate data, then of course you can't hope that the policy will be optimal. It will be optimal for the model that you have learned, and that might be suboptimal. Okay, just a quick note on an extension, an interesting extension maybe of this DynaQ algorithm called DynaQ Plus that addresses the problem of good exploration and intelligent exploration to some degree, really, where you basically give an exploration bonus. Yeah, so rather than just giving a reward, the task reward, the immediate reward, you also have a weighted exploration bonus, tau here, that's weighted by some weight kappa. And yeah, so it depends on the number of time steps for which you haven't visited a certain transition. Yeah, so things that you haven't explored, state and action combinations that you haven't explored for a while, for those you get additional bonus if you visit them again. Yeah, so to make sure that you don't miss any changes in your environment, and you don't completely leave out certain regions of your state and action space. So that's what this DynaQ Plus does, and the effect of it is can be seen on this slide. So in general, so you have on top you have these little grid worlds again. You have a starting state and a goal state, and in this case there's a wall blocking almost the whole passage, but only to the very right there's a somewhere the agent can come through. And it needs some exploration, of course, to find that. And you can see that DynaQ is faster in doing that compared to the regular Dyna. that doesn't have this incentive, right? This exploration bonus. So it's faster in the beginning, and then at this time step 1000, the environment is switched so that the whole wall is moved to the right. Yeah, so it basically blocks the passage that was there before, and it opens the passage on the very left. Yeah? So now there's then in the beginning, it takes some time until the agent really realizes that this solution is no longer available, right? It will still try to go there and needs some time to explore new regions of the state space and back up the values that are no longer good here. And then, so after a while, it makes progress again, and then both have similar dynamics. But so that's faster learning for DynaQ, especially in the beginning. But then also in this case, on the right that you see here, again, you have the setup as we had it here with the passage on the left open. But then after 3000 time steps, the environment is changed so that all of a sudden there's a better solution available, right? So there's a shorter path going from S to G rather than taking this detour around here. And DynaQ will have an easier time because of this exploration bonus to actually visit this state again and find the better solution and make faster progress, as you see here. Yeah? Okay. Maybe again, just to see if there's any questions, we stop briefly. Concerning Dyna, is there any question? Good. Then we'll come to this last part, just a few slides to briefly introduce the concept of Monte Carlo tree search or simulation-based search more generally, right? So this, as I said, these ideas from Monte Carlo tree search are really very powerful and very successful in various domains in the reinforcement learning literature. And they are model-based, yeah. So they use a model to basically simulate forward what might happen. So you concentrate, you don't update your whole state space, but you build up a tree of experience over time, yeah. And you basically say, at this current step where I am right now, what would be possibilities, possible scenarios like we talked about before, Moritz. So the different ways to call this, rolling out different possibilities of what might happen in the future with your model. Yeah. So you use this so-called forward search. Yeah. So you start at a particular point, and then you do rollouts with the policy and see what might happen as predicted by your model. Yeah. So you start from now. Okay. So now is the state ST, and you use your model to see what potential futures might hold for you. And then again, you can apply model free RL to these simulated episodes to basically store the experience that you've gathered with these random rollouts and amortize them in your Q values. Okay, so Monte Carlo tree search really does this by building a search tree step by step for the visited states and the actions that were executed using the model, right? So you will be at that state, and then you can ask, if I execute this action, where will I end up in? You ask the model, so you simulate episodes from your current state with a so-called tree policy, yeah, that can maximize over the Q values in your tree nodes that you've already visited. Yeah, so there you can do something like epsilon greedy on those Q values. Whereas, once you get to a leaf node in your tree, as we'll see in the next slide, you don't have valid Q values yet, right? Then you need to then what you do is basically just do random rollouts from there. Yeah, just Monte Carlo rollout and see what happens with some random policy, for instance. But you can still, of course, use that Monte Carlo rollout experience to then propagate up again through all the nodes in your tree that were part of the trajectory. Okay, and yeah, as mentioned several times now, this was one vital ingredient to this AlphaGo success story in 2016. So how does it work? It has these 4 steps. Selecting a node, yeah. So this will be the root of our tree, and we then traverse to a leaf node following this so-called tree policy, yeah. So as long as we have nodes that we have valid Q values for, that we have already visited and we have Q values for it, we can use something like epsilon greedy to derive an in-tree policy or tree policy. Then we will get to a point where we could expand the tree, yeah, and we usually expand it by 1 or multiple child nodes, and that we might get to after some iterations. And then we do a rollout from that newly expanded node. Yeah? And these rollouts, the returns that we get from them in these Monte Carlo rollouts, we will then back them up again for the action values of all the nodes that were part of our trajectory through the tree. Yeah? So here you have this again in pictorial form, these 4 steps. So first, we select a node, and from that node, we will expand. We will use our tree policy, yeah, that we can do epsilon greedy on the Q values associated with the different nodes. So for instance, we start here, we decide to go left, then we decide to go right. Then, here we could either follow along, or we can then decide maybe it's good to take that action here. So we expand our tree by 1 more node to the left here. And now this is a leaf node. That means we can now do a simulation. We just do a rollout with our potentially random policy. Doesn't necessarily need to be random, but it's often done in a random fashion. And then we just see where we end up in, what will be the return at the very end. And that's a Monte Carlo return that we can then just back up again to the Q values to the earlier nodes in the tree. Yeah? So by these steps, we slowly build up our tree or parts of the tree. Yeah? We don't need to generate a whole tree. This is more like, step by step, you build parts of the tree from a given node that you're interested in. And then you use your model to explore, to first traverse the tree in some promising way with your tree policy. You decide where you want to expand, and then you basically want to forward simulate up to a certain horizon in order to gather new experience that you can back up. Yeah. Okay. Yeah, and that's basic. That's the basics of this Monte Carlo tree search. In AlphaGo, it was additionally extended with some other ideas, where you would also learn a policy to select these nodes in the tree that you would want to examine and start your expansion from and do the simulation from. And you would also learn values that can give you that were mixed with the Monte Carlo returns that you would get. So it was much more intricate, and it was using first supervised training of a policy from human games in the first AlphaGo systems. Later on, they did it completely without human data, and it actually worked even better. But in the first version, they relied on historical data from humans, where they trained it in a supervised way. And then they did policy gradient in order to train this the selection policy based on really, again, the raw board configuration without giving features, yeah, but learning features through this deep reinforcement learning approach directly for the policy and the value function from the raw board configuration. And that was also very important in order to get to good recommendations for selection of the nodes in the Monte Carlo tree. Okay, that's just, in a nutshell, what worked there. Okay, and that's it for now. That's what I wanted to talk about regarding model-based RL or planning and learning. Let me see if there's questions. Yeah.